So something else that we're looking at in this chapter and this is going to be related to conditional proofs, is logical truths. So first, some vocabulary stuff. A theory is a set of sentences called theorems, and our theory of propositional logic can be characterized either by the set of its theorems or by the set of its logical truths. Since all theorems are logical truths and all logical truths are theorems, so that goes both ways. There are two ways to show that a given well-formed formula is a logical truth and hence a theorem of propositional logic. One, this should be a one, semantically by means of the truth table, which you all know how to do a truth table, and something will be a logical truth if the major operator for some expression is true in every single row. It's impossible for it to be false. And two, proof theoretically by means of a derivation. And that's what we're going to be talking about here. So to show that a well-formed formula is a theorem of propositional logic by means of a derivation, we use the method of conditional proof, constructing a derivation, in this case, with no premises. So we start in the previous examples, we started with some premise and there was a conclusion that we wanted to show. So the first thing, or something that we would do, is in the course of working through that proof, we would stop at some point and indent and show that we're working through a conditional proof where we assume something and see what follows from that. And then we discharge. If that was true, then something else was true. And then we can either finish our proof if that's what we were looking for or keep going from there. Um, but that also works if we don't have any premises. We can just assume something and see what follows from that assumption given the rules. So in this case, we're going to start already indented. The very first line of our premise here is already going to be indented. So we want to prove that one of my parentheses is flipped around here, but hopefully that's not too distracting. Prove that S or P and if S or P and Q, then S or Q is a logical truth. So you can see that the logical what we're looking to show here is itself conditional, which is going to make sense because uh, really all we're saying is if it was true that S or P and Q, then it would be true that S or Q. Now, if you think about some of these logical truths, they'll seem like just examples of some of the rules that we were given before, like things like hypothetical syllogism or disjunctive syllogism or whatever. The reason that these are rules that work is because certain things will entail any instance of them, or will be entailed in any instance of them. So we're going to start our conditional proof with the antecedent of the conditional that we want to show. And the conditional that we want to show is this logical truth that we're being asked to prove. So our assumption is just the antecedent. If S or P and Q, and if we start with S or P and Q, we want to see if we can get to, using our rules of inference and equivalence, S or Q. Now, if we can find S or Q using these rules, starting with just this assumption, then that tells us that if it were true that S or P and Q, then it would be true that S or Q, regardless of what the values of S or P or Q or whatever actually are. But we're just talking about a relation of if they were true, then this would follow. So our first line is the antecedent of the conditional that we're looking for. Now, something that we can do with this here is to distribute. So we have S or P and Q. So we can apply distribution to that line. So we get S or P and S or Q. It should be fairly obvious where to go from here. Next thing we'll use is commutativity. On line 3, we'll swap these around so we get the S or Q in front. Then we just simplify the S or Q to get it by itself. And it turns out on line 4, we have the consequence of the conditional statement that we were looking for, which means that we can go ahead and discharge our conditional proof, which is here going to be if S or P and Q, then S or Q, which is exactly the logical truth that we were looking to show. And our justification here should be 1 to 4 conditional proof. I had some um, find and replace issues, I think, when I was working on these slides. That this is why it's showing up that way. I'm waving my hands around about this so that you notice. Hopefully, you don't think anything too weird's going on. This should, instead of T through 4 conditional proof, it should be lines 1 through 4 conditional proof, and this other parentheses here should be swapped around. Hopefully, if that's not too confusing, then everything else here should be pretty straightforward. So, to see that a logical truth is a logical truth, if you want to really check it out, well, you can go ahead and put it in a truth table. So, here we have the exact statement that we were asked to show as a logical truth before. And you can see this would be a pretty big truth table if you wanted to do one. It's going to have 8 rows since we have 3 variables here, and it would take a long time to fill out, and it would be really boring. But if you actually do that, you can see that, well, the major operator here, the conditional, it's going to be true in every single row. It's just, regardless of what the values of S, P, or Q are, this relation is going to hold that if it was true that S or P and Q, then it would be true that S or Q. That's just always going to be the case. All right, so something to be careful of here, when constructing premise-free conditional proofs, you may begin by assuming any well-formed formula. You can assume whatever you want. However, it is never useful to assume the desired conclusion. So if we were trying to prove that S or P and Q, if S or P and Q, then S or Q, and we begin by assuming S or P and Q, if we begin by just assuming the entire thing, it will discharge as a conditional with the desired conclusion as the antecedent. So it seems like, well, if we want to show that something is a logical truth, can we just assume that the whole thing itself is true? And we could, but the conclusion, or what we end up getting to when we discharge is not actually this. We can't just assume the first line and say, look, we assume the first line, it's true. What we want to show with a conditional proof is a relation between the assumption and something else that we derive from that assumption. So it wouldn't be helpful if we're trying to prove this whole thing, we wouldn't assume the entire thing, because then it would just say, like, if this whole thing were true, then something else would be true, but that's not what we're trying to prove. So we want to be careful here and only assume the antecedent as our first line, and that way it'll discharge as the antecedent of a conditional when we're done. And we see if we can find the conclusion or the consequence of this conditional statement using our conditional proof. So if we assume S or P and Q, if S or P and Q, then S or Q, and we're doing a conditional proof with that as our first line, what we're really showing is that, well, something else follows from that, but that's not what we're trying to show. So one of the 4 laws of thought is the law of the excluded middle, which states that any claim of the form alpha or not alpha is a tautology. So a tautology is something that's just true, always. So if I say alpha or not alpha, well, either alpha is true or not alpha is true. That's always going to be the case, that one of these two things is true. And that's just an expression of what we call the law of excluded middle, where you have one thing and its negation. I think I talked about this earlier on in the lectures toward the beginning. But if you have something or its negation, there's no third possibility. Either alpha is true or not alpha is true. So if we have a disjunction between the two, it's the disjunction itself is always going to be true. All right. So we can prove the law of excluded middle. This is one of those things that four laws of thought are often taken to just be sort of brute facts about how we think about things. The law of the excluded middle here being one that we can show in this way. Others are more difficult. For example, one of them is the principle of identity, which is just that a thing is what it is and it is not what it is not, which is required to make statements like alpha or not alpha in the first place. That things are what they are and they're not what they're not, and we don't confuse their identities in that way. Yeah, so some of those that one's sort of more difficult to prove. Aristotle famously said he didn't prove it so much, but he said, well, anyone who ever says anything assumes the principle of identity, where if you would open your mouth to say something, then you're asserting something, you're intending to assert something, and you're not intending to assert what you're not asserting. So there's a sort of, it would be difficult for us to do anything if the principle of identity didn't hold. And some other commentator, I can't remember his name, I think it was an Arab scholar, not too long after Aristotle, had a more extreme take on the principle of identity, where he said that, well, if anyone would assert that the principle of identity doesn't hold, then you can go ahead and set him on fire for him. Being on fire is the same as not being on fire. You can starve him for starving is the same as not starving. You can do anything to him because it's the same as not doing it to him. And then see if he comes around to agreeing with the principle of identity. Anyway, that's a sidetrack there. But back to the law of excluded middle, we can show some proof within our system for the law of the excluded middle, where for anything, either it or its negation is true. So first, we'll assume P. Remember, we're indenting P. And then with our assumption P, well, we discharge it immediately, and we get, well, if P, then P. So here, because our conditional proof is just one line, the first line is also the last line, so it is both the antecedent and the consequent of the conditional that we get. So if there's a P, then if P, then P, and then we can use material implication for if P, then P, and if we do that, we get not P or P. So either not P is true or P is true, and there's no third term. And we can flip these around to get P or not P with commutativity, and we're done. This is an expression of the law of excluded middle. It's always going to be the case that for some statement, either it is true or it is not. In systems, anyway, that have bivalent truth values. And there are, like I said, some systems in which it's possible for there to be true contradictions. We're not going to worry about that, though. This isn't one of them. All right, so next, converting ordinary derivations into logical truths. So for every valid argument requiring premises, we can create a proof of a purely logical truth. So we can join all of the premises into one statement, then write a conditional that takes the conjunction of the premises as the antecedent and the conclusion of the argument as the consequent. Or we form a series of nested conditionals, using each premise as an antecedent and the conclusion as the final consequent. So, for example, converting as a valid argument form, modus ponens can be converted into a metalinguistic logical truth. And a lot of these logical truths are really just ways of showing that our rules of inference and so on are actually always true. So if we take this statement, which is if alpha then beta, and alpha then beta, which is what we have inside the premises, or inside the parentheses for the antecedent of this conditional, are really just both of the premises that we would need for modus ponens to be the case. If it was true that if alpha, then beta, and it was true that alpha, then we get to beta. So this is just an example of modus ponens. But we can also express it this way. If alpha then beta, if it's true that if alpha then beta, then if alpha then beta. But now this looks a little bit sort of more straightforward and obvious, maybe, but the relation between this second way of showing this and modus ponens is a little bit less clear. It's a little bit more opaque. But both of these are ways of expressing the modus ponens relation as a logical truth. So we can also do the same thing with hypothetical syllogism, which here we're going to start getting a bunch of conditionals. We get if it's true that S and P, and it's true that if P then Q, then it's true that if S then Q. Which, again, everything that we're looking at on the antecedent side should just be a conjunction of the premises that would be required in order to get to the consequent here, which we would be able to get to with hypothetical syllogism. And again, this can be expressed in the same way as before, where if it's true that if S then P, then it's true that if P then Q, then if S then Q. All right. So here's an example. We'll prove the converted hypothetical syllogism using the method of conjoined premises. So our assumption in the first place is going to be if S then P and if P then Q. So we're just assuming, well, these are going to be the premises that we need, and we'll see if we can get to the result that we want with hypothetical syllogism. To show that the relation between these premises and the result that we want, that hypothetical syllogism indicates, if we can get there with just this assumption. So our second step here is we can go ahead and simplify to get if S then P by itself. Then we'll use commutativity on the first line to get if P then Q up front. Then we'll simplify again to get if P then Q by itself. This is one of those instances where you'll probably find it real annoying to have to do all of these steps because, well, you can just see in premise 1, all of these things that we spent 4 steps doing to get have already been given, but it's important to do things one step at a time. So if it's true that if S then P, and it's true that if P then Q, then with 2 and 4 through hypothetical syllogism, we get if S then Q. So then we discharge the relation. Remember, we were doing a conditional proof in the first place, so we have to discharge. And when we discharge our conditional proof, we get a conditional of the form where we take the first line, and the first line of our conditional proof, the entire thing, we have a couple, no matter how complicated it is, how complex the well-formed formula of the first line is, we take the entire thing and put it in parentheses, and that'll be the antecedent of a conditional statement. And then we take the entire last line and put it in parentheses, and that'll be the consequent of a conditional statement. So we get if S then P, if it's true that if S then P and if P then Q, then it's true that if S then Q, and that'll be lines 1 through 5, conditional proof. All right. So all 10 rules of equivalence can also be turned into logical truths even more easily. We can just replace the metalinguistic symbol with these 2 arrows. We can replace it with a biconditional. So for example, with double negation, alpha is equivalent to not alpha, and P is P if and only if not P. And for any other more complex well-formed formula, this is always going to be the case. So they're just equivalent with each other. All right, next in the next video, we'll do indirect proof, which is another different kind of subproof.